Jumping back into part 3 of the module 1 math from test 1. This is where I'm getting it over here. So again, this is the paper tests that are on the College Board site that you can download as PDFs. This is going to be module 1 of the math part 3. So this is going to be the latter part of the test. So there's only a couple more problems left to do here, but they are really good problems. So let's try to jump into 23 here. So when I see this, I'm already thinking kind of unit manipulation, right? I see 4.36 square miles. So I want to put a lot of emphasis on that. These are square miles, not just miles. So as opposed to a length, this is going to be an area, right? So two multiplications. What is the area in square yards? Okay, so at least that's relative. Square miles, square yards, they're both square or have two types of units. Square yards of this town. So we're never going to have to know like yards to miles, anything like that. They give us a translation here. But I want to be really careful with this translation. This is telling me miles to yards, which is a length to a length, not area to area. So the easiest way to do this is to just change my translator instead of length to length. Why don't we just make this area to area? So if I square both of these, what that would tell me is 1 mile squared is now equal to, let's plug this in the calculator, 1760 times 1760. And I should get 3,100,000, something like that. So 3,100,000. So I'm rounding just to make it easier to write. So I should get something like this. So now I can say this is yards squared. So that's really important that we make that distinction. We have changed our translating units from length to area to area now. So I know for each mile, I'm getting about 3 million yards. Well, how many miles squared do I have? And I have 4.36 square miles. So then I could say, okay, well then 4.36 miles squared should equal what? And to try to make this proportion make sense, it looks like I have to multiply by 4.36 to get to that. So then I should also multiply on my other side. So if I multiply that by 4.36, and I mean the 3 million yards, I should end up with 13 million-ish yards. So keep your units consistent, change your translator, your 1 mile to 1760 yards into area, and then you just have to go that little extra step. Oh, they want 4.36 miles squared, not 1 mile squared. Multiply the 3 million by the 4.36, and I get D here. Pretty good way to start off this module. These next couple problems are tough, very tough. So let's start with this. Actually, the last two are really tough. These two are okay. When I see these two, or when I see this problem and I see these kind of two columns, I'm already thinking this is probably going to be a line, right? They say for line H, the table shows. So let's really signify this is going to be line H here. 3 values of X and their corresponding values of Y. Line K is the result of translating. Okay, so we have another line. Line K is translating H down 5 units. So that would just be H minus 5. So remember when they translate up, it's plus 5. Translate down, it's minus 5. That's the easier type of translating, right? So I can get a line from points, right? I could do like x2 minus x, or y2 minus y1 over x2 minus x1. But we can also just use Desmos here, right? Let me go ahead and pull up Desmos real quick, and let's see if that makes this type of table problem easier. I think I did an example like this on one of the extra math worksheets, but not on these modules yet. So if I pull up Desmos here, let's try to move it just so I can see the table just like that. And you see this little plus sign here? I'm just going to throw in table, and I only need 2 points to get a line. So I throw in these 2 points here, and I should get, I should see this kind of line with the 4 dots off to the left. If I click on that, it gives me a line right here, y equals 6x plus 22. I'm going to go ahead and just write that on my table up above here. Y equals 6x plus 22. Okay, so you can just see Desmos is going to really help us in a lot of these problems, whether it's a table, whether it's system of equations. So remember, that's line H though. For line K, it's H minus 5. So I literally just go 6x plus 17 because I'm taking 5 away from that line. So this is now line K, and they just want the x-intercept. It kind of gives it away. When I see a 6 and I see a 17, well, it's probably going to be D, right? Because I'm just solving for my x. So if I subtract the 17 over, I get negative 17. I divide by 6, and I should get D here. So again, 24, really good problem to practice. Got D. Let's try 25 before the two final really hard problems. So 25, let's go ahead and move this over. Well, this might be similar to 24 in a couple ways. So I see the graph of an equation, I see a parabola, and I see it intersects this line y equals c at exactly 1 point. This language is going to be extremely important here. So when they say that it intersects this line y equals c, well, usually it's like y equals x, or it's like some form of like a linear equation. But when it's y equals c, or y equals a, or y equals b, those letters are always used for constants. So y equals c is actually something similar to y equals 5. And if I tried to graph that, we want to be very clear on our kind of two more odd linear equations. We're going to have a linear equation that looks like this, and we're going to have a linear equation that looks like this. If I said this was at x equals 5, well, that's actually the line. This would be the line, x equals 5. And if I said this was at y equals 5, that is also the line, y equals 5. So when it is a y equals 5, we get a horizontal line at 5. When it is x equals 5, we would get a vertical line at x equals 5. So in this example, we see we're going to have the green line here. So I'm going to go ahead and get rid of this. And then I also want to recognize if I just drew a random parabola, right, like this, and I try to, it's not letting me move it. So let me redraw it up above. When am I going to get a parabola where it intersects at exactly 1 point? Like if I drew it like this, well, that's 2 intersection points, right? If I drew it like a little bit further up, that's still going to be 2 intersection points. If I drew it below, that's going to be 0 intersection points. There has to be exactly one time when it's going to be 1 intersection point, and that's going to be when it intersects at the vertex, correct? So that actually makes this problem really easy. I just pull up Desmos again, and we graph the parabola they give us, right? So if I just say, okay, y equals negative x to the second plus 9x minus 100. So we're going to have to find it. You always just zoom out a couple times. I know it's going to be pretty far down there because of my minus 100. And I have my parabola. If I know that this parabola is intersecting my horizontal line at the vertex, right? Can I just click on my vertex here? And I'll just write it off to the side here. I see 4.5 and negative 79.75. So I'll minimize Desmos again because it got me all the information I needed. Even though there's 2 lines intersecting, I don't need to draw my second line because I know it's intersecting at a known point, the vertex. And then I have to ask myself, well, what's going to be important here, the x or the y of my vertex? And we know it's going to be the y because it's y equals c. So at this line, it's actually not y equals 5. It's going to be at negative 79.75 on my y-axis. We are going to have a parabola that the vertex hits at that point, and a horizontal line is going to hit at that point. I go through my answers. I plug in, well, I don't exactly know negative 79.75, so I do 41 divided by 4, that's 120. 319 divided by 4 is going to get me my 79.75. So what kind of seemed like maybe a more confusing problem turned out to be pretty easy. Graph your parabola, exactly 1 point at the vertex. You find your vertex, you just choose your x or your y, depending on the equation that they're asking for, and they ask for y. Okay, now let's jump on to the 2 hard ones. At least 26 is a really rough one. This is a super unique problem. So what are they asking for in number 26? Let's go ahead and look through it. They're starting off with 2 equations here. 2x plus 3y equals 7, 10x plus 15y equals 35. At first, I might think this is like a really simple system of equations, right? I don't think they'd be saving that for number 26. I know on these practice sheets, it's a little bit longer than the actual blue books. I think the blue books stop at 22. These go to 27, which is good. It's a little bit extra practice. But I digress. Later on, these last few problems are not going to be easy problems. So it might not be a system of equations. If you did plug this into Desmos, though, which I think is fine to try, you'll see that these two actually end up being the same line because this equation is just this one times 5, right? Times 5, times 5, times 5. So they're actually the same line. Let's look at what they ask from us. They say for each real number r, so r could be 1, could be 2, could be 3, which of the following points, okay, cool, so these are just points down below. You know, this would be like an x, and then I see a comma, and then I see a y. Which of these points lies on the graph of each equation in the xy plane? Well, it is nice of them that they gave us the same lines because I actually only need to match it to 1. I'll try to make up a problem where they are 2 different lines because that would be really hard. Same equation, so I only need to do 1. I do the simplified version. And this is where we have to really think. How would I know if one of my answer choices fits on this line? Because there's so many variables. I have x's, I have y's, and I have r's now. The first inclination that we want to build, this habit, is looking at my answer choices, what would we rather start with? Because there are just some problems that the process of discovering your solution is answer inferred, right? Which one of these is the most complicated? And it's by far A, right? A has a relationship in the x and has a relationship in the y. So if I was going to plug this into my line to see if it worked, and you'll understand what I'm saying in a second, that would be the hardest one to test. So I look at B, and let's explain a little bit further by what I mean by easier to test. I look at B and I see I have an X, and then I have a comma, and I have a Y. Up above in point A, I had a lot going on with X and a lot going on with Y. In B, I have a lot going on with X, but for my Y, it's just R. So think about that. If I try to plug this in, should it not make a functioning relationship? So I go up above and I say, okay, 2x plus 3, and I plug in the easy one, 3r, because my y is equal to r in letter choice B, and this is equal to 7. So instead of plugging in the x, which I could, but I'll have to do distribution, what if I just solve for x and see if I get the x and b? So I solve for x, and I get 3, or that would be solving for r. We want to solve for x. So I get 2x is equal to negative 3r plus 7. Divide by 2, and I get x. Now, this is going to be one of those problems that when you see it now, it's like, wow, this actually looks really easy, and that's good. That's the whole point of practicing. Look at my x point, or my x coordinate, and b, negative 3r over 2 plus 7 over 2. This works. We got lucky. The first one we tested works. The strategy for these types of problems, skip the hardest ones. Try the more simple ones where either your x or your y are just going to be r. Just for practice, let's test C, let's test D, let's see what we get. This is going to be one of those ones that kind of just repetition is going to make it easier in our minds. Try this one again. Go back, pause it, try it. Let's go ahead and test C to see if it works. So in C, it's different. They're saying my x is r, and then my y is this complicated point. So remember, plug in your easy point. I go up above. My r is going to be x, so 2r is going to be equal to, or sorry, not equal to, plus 3y. And that's going to be equal to 7. Now, again, we're solving for the y to see if it matches up with this guy. So 3y is equal to negative 2r plus 7, divide by 3, and I'll scroll down a little bit. And we can see that I get 2r over 3 plus 7/3. So it's just these little tiny differences they're going to have in their other answers that make all the difference. This one does not work. You can try D and you can try A as well for practice, but you're going to see that only one of our answer choices are going to make our relationship function. Really good practice problem. I'll have extra examples of this in the future because I think this could be an even tougher problem if our equations up above were not the same. But let's try this last one. I don't think this one's as hard or as abstract, but it's still a good one to practice. I see number 27 here. And I see an equilateral triangle. Always, I'm just drawing it right off the bat. And let's move my camera out of the way. And they give us a perimeter. That's nice. So they say my perimeter is 6, 2, 4. Well, remember, perimeter is all my sides added up. So I just divide that by 3. And I get 208, 208, and 208. All right, not bad so far. And they say the height of this triangle, so that's nice. They already, you know, anytime I do see a shape, remember, we always want to figure out if I can make a right triangle. I can't solve really too many other shapes other than right triangles. So they do it for us. They give us a height, and this height's going to be k square root of 3. Where k is a constant, what is the value of k? Okay, so there's multiple ways we could look at this. Remember, right triangles is everything. So I try to kind of re-look at this, and this is actually just going to be 104, right? I don't care about the measurements of the equilateral triangle. I want to solve right triangles. So as soon as I see this, there's going to be kind of like a shortcut here in a solving way. I say we do it the solving way, just so you always have a backup plan, and then we'll do it the kind of the shortcut way. So if I look at this triangle now, I'm going to scroll down a little bit so I have some space. I have a side, and I don't know my third side. Pythagorean's theorem, right? So I should just be able to do 104 squared plus k square root of 3, remember to surround it in parentheses, squared, is going to be equal to 204 squared, right? So let's go ahead and get rid of this so I can fill in a little bit more space. So if I solve for this, I should get, what I'll just do is I'll do 204 squared minus 104 squared in my calculator. Minus 104. Okay, so I get equals 32,000. So 32,448. And then on the left side, we still have k squared times 3. So remember, you have to distribute your squared. K gets squared and square root of 3 gets squared. And that turns into k squared and 3. So now I just divide that number by 3. And I should get, I'm just going to erase this so I get more space. And I should get k is equal to, or actually k squared is equal to 10,816. And again, we would just take the square root, right? Square root of this. Well, they changed the calculator. But I know that the square root of this is going to be 104. So k is going to equal 104 here. And yeah, I don't think that was too bad to solve that way. I think that you could still solve this in under your time limit organically like this. So this would just be, I erase k here. This is just going to be 104. Now in terms of shortcuts, maybe you recognized it, maybe you didn't. We're going to have a lot of special triangles on this test. And one of our special triangles, you'll have to go through all the material to find them all. But one of our special triangles is going to be a certain right triangle. I'll draw it down below here. And this special right triangle is going to be a 30, 60, 90. So nice and neat and even, right? So if this is a 30, this is a 60, and this is a 90. This is going to have a certain relationship. What we would have is we would have a 2x on this side. And here's like an easier way to remember it. Let me scroll down a little bit more. An easier way to remember this is one of your sides is going to be x, and one of your sides is going to be square root of 3x, or x squared of 3. Just remember that your 60 is going to represent your bigger side, right? So I just think of it as the 60 gets this, and then the x would go with the 30 because the angles are directly correlated to the sides. So the 30 gets the x, the 60 gets the x squared of 3, and then if I compare it to my triangle up above, well, we would know our angles immediately, right? The 60 would go here because it gets the one with the square root of 3, and then the 30 goes here. So if you ever see triangles with the square root of 3 on one of their sides, consider it could be your 30, 60, 90 triangle, and it should be this relationship. So yeah, great problems. We'll jump into Module 2 of Math tomorrow.